Thank you very much. So I would like to talk about this view on teleparallelism from liquid crystal perspective, which is very similar. So like in liquid crystals, we have these molecules as three different axes. Yeah, so like one log axis and also recognizing the twist of this axis. So this is very popular in liquid crystals, generally called Landau-de Gennes model. I based on. So as you in teleparallelism use the four vector fields being orthogonal, here we can pack them into one tensor field. Yeah, so we take the 3 or 4 vector fields and pack them into one tensor field, but it requires that we distinguish their length. We need to distinguish the four vector fields. So I would say that it's crucial also to get the different forces. Yeah, so like here in 3 dimensions, we get 3 different axes, a long axis and twist. And going to 4 dimension, the space-time, we get also zeroed axis. It should be much longer. So finally, from this dynamics of 4 axes, 4 vector fields, we get both the dynamics of these boosts of this time axis. Will be very tiny boosts of the time axis, and they will correspond to gravity electromagnetism. The second Maxwell equations for gravity. Then in space we have this long axis, which like here performs a hedgehog, and hedgehog is topological charge, and they obtain Coulomb-like interaction for this kind of quantized topologically charges. Yeah, so we get electromagnetism for this second axis, which works in space, and finally it recognizes the twists, and these twists correspond to the lowest energy. Yeah, so finally, for example, if you look at quantum electrodynamics Lagrangian, we have both electromagnetic term and much lower contribution of quantum phase evolution. Yeah, so we need both. We need to unify them, and to emphasize that they correspond to completely different energies. We have these lambdas, this shape of molecule, saying that the 4 axes are different. They have, let's say, different length, which contribute to these different contributions to Lagrangian Hamiltonian. Yes. Okay. So one more time, you have 4 axes. The time axis is the zeroed axis is toward time, and its tiny boost corresponds to gravity. That they are governed by Maxwell equations through gravity electromagnetism. Then we have these tilts as for second axis. Now these are in space, and it gives quantized charges as topological, like this hedgehog, and we get Coulomb-like interaction for them. I talk about it, and finally there are also twists, very tiny energy dynamics governed by close equation, the Klein-Gordon-like equation, to unify all 3. Yeah, so finally, from this dynamics of this tetrad, 4 vectors, you get unification of gravity plus electromagnetism plus quantum phase evolution. Yes. So I believe this way we can finally make happen this Einstein's dream of unification of gravity with electromagnetism, with the main difference that we recognize the four vectors. They are not the same. They correspond to different lengths as energy contributions in Lagrangian. Yeah, so maybe this is second as the first slide, but from a particle perspective. So this is asking for a non-perturbative model of particles. So we would like to go even lower than quantum thermodynamics. So in perturbative approximation, we have these Feynman diagrams. We kind of represent particles as a result of creation operator. But in non-perturbative, there should be fields. It should represent some field configuration. So we will ask for this field configuration of particles. And the most crucial here is this charge quantization. That electric charge with standard Gauss law is not quantized. It's a real number. Why in nature it is integer multiplicity of elementary charge. So if you have the Gauss law, it counts that the electric charge being a real number. In nature, it is integer number. So there is topological version of Gauss law. It's called Gauss-Bonnet theorem, which looks very similar, but instead of electric field, it uses curvature of some deeper field. Yes, and this will be exactly this curvature of the second axis of this tetrad, of Einstein's tetrad. So if we call this curvature of the second axis as our electric field, then the Gauss law will count the topological charge of this field, yes, and getting like elementary charge for this hedgehog. Yeah, so this is the main motivation, to repair the Gauss law, to make it have built-in charge quantization as topological by interpretation of curvature of deeper field as electric field. Yes, this way the Gauss law counts topological charge. So here is the Lagrangian I'm finally focused on, as promising to unify all the forces, electromagnetic, gravity, and quantum phase evolution. So we need this electromagnetic-like term, like F mini, but interpreting this F as curvature of deeper field. Yeah, so we have this deeper field, this M tensor packing the four vectors finally, and we interpret this curvature as our F tensor, and use standard electromagnetic like term for this F tensor as curvature. Plus, we need also Higgs-like potential. So Higgs-like potential is required to regularize the singularities. That there is some shape, but in the center of singularity, like a center of charge, we need to deform the defect. If we don't do it, we get infinite energy. Yeah, so it's crucial to have this Higgs-like potential, which literally prefers some shape of the molecules of the four lambdas, but allows also to deform them, avoiding the infinity and adding and giving particles mass. Yeah, so this also. So finally we need kind of Lagrangian with F tensor as curvature of a deeper field, and it indeed will unify all the three forces and will give particles as topological excitations. So first of all, the topological charges for electric charge quantized, and also topological vortices, which are also crucial in particle physics as quark strings, for example, connecting quark anti-quark part. So I also talk about it. Okay, so maybe let me skip. So this is another view, but maybe let me skip it. So very briefly, maybe the mathematics, but I will talk further. But this is liquid crystal view. Yeah, so liquid crystal people first start with this kind of field of just unitary vectors, and so this is called Austin-Frank model, and they guess some energy, as we can say Hamiltonian. So then we need to go to this biaxial nematic, that we recognize the three axes. Yeah, so this is only one axis. Now we would like to recognize the three axes, and this is the dimension Landau de Gennes model. Yeah, so who got Nobel Prize. So we literally have some shape of molecule. Here 3 lambdas. Finally, we would like to use 4 lambdas in teleparallelism, and we need this Higgs-like potential, which prefers the lambdas, the shape of our molecule. Yeah, so it makes that the four vectors are different, but also allows to deform the singularities in the center of charge. Yeah, so finally I will go to this kind of Lagrangian. But let me start from the beginning. So regarding the electron, so it is seen in standard perturbative approximation as a result of creation operator. However, it is extremely complicated configuration of electromagnetic field, especially. Yeah, so it is not only electric charge, what means some very concrete electric field configuration. It is also magnetic dipole moment. Yeah, so this is also very concrete magnetic field configuration. Also, it is gyroscope. It has angular momentum, so like the gyroscope, but this is not rotation of point. We have only fields. So this angular momentum is in fields. Yeah, so thinking about point rotating makes no sense, but we have field configurations only. So this angular momentum is in the fields, conserved to the nether theorems. Additionally, it also has the clock, so it's called the Broglie clock, Zitterbewegung. So it is required in relativistic quantum mechanics that in the phase evolution we need to use energy being the mass mc square. Yes. So literally the mass of particle of electron, also neutrino, the mass of particle literally propels the clock. Yeah, so we also need this mechanism, and I will talk about it also. Yeah, so it is in this Lagrangian I'm talking about. We get this kind of mechanism. So here is the experimental verification of this clock of electron. So 2008 article, this one. So they use high energy electron, ATMF electrons, and thanks of that, the distance between ticks of the clock should agree with lattice of silicon crystal. And getting this agreement, this resonance between clock and the spatial lattice, they get increased absorption. Yeah, so literally they observe this clock of electron. Yeah, so this is another thing we need to get in our model. So I will also talk about it, and it is obtained here. So finally, I mentioned that this field configuration seems in agreement with electron properties. Yeah, so from one side, as mentioned, it has quantized charge, which acts as quantized electric charge, topological charge. So the long axis makes a hedgehog, which acts as a topological charge we interpret as electric charge. Yeah, so we will get Coulomb interaction soon for them. So from the other side, we recognize this twist, and this twist has to evolve in time. Yeah, so now with time we assume that this field twists. So interpreting it as the quantum phase, we get this kind of quantum phase evolution as we need for relativistic quantum mechanics. Moreover, this twisting also acts as angular momentum. Yes, and also we see that it also will bring the magnetic field. Yeah, so finally, this kind of hedgehog for quantized electric charge as topological, plus this constant continuous phase twist, we combines the three properties. Yes, both the magnetic dipole moment, angular momentum, and the clock. Yes, this is phase evolution. So second particle for which we know that there is some oscillation is the neutrino. Yeah, so again it is seen as a perfect point, but for example, there is this recent article showing that in fact it is like six picometers. There is like 1,000 times larger than nucleus. This is wave packet, but still we should ask what is the field configuration hidden in this huge size. So I will also talk about it. Okay, so let's go to the concrete models of solitons as particles. So for the solitons, it is good to start with the sine-Gordon model. Very simple one-dimensional model. Just you can realize with just lattice of pendula. There is some YouTube video you can watch. That so we have this lattice of pendula. All pendula due to gravity want to be down. However, there is one down and there is another down 2 pi further. Yeah, so we have many vacua. Yeah, so and we can go from one vacuum to another vacuum, and this configuration is stable and it hides energy like particle. Yeah, so this is a simplest particle in one-dimensional 1 plus 1 dimensional model. So it already has special relativity. So here is resting particle, here is moving particle, and you can see Lorentz contraction. So literally we can recreate an entire special relativity with this simple mechanical model. So we have this is phase. We have these two minima. So here is one minimum, here is second minimum. The kink is like particle, massive particle goes from one vacuum to another, minimizing energy. Yeah. So this is some shape of this molecule of the particle minimizing energy. So there are these massless excitations, photons, which travel the maximum speed, but there is also massive, which are restricted by special relativity. So we get exactly with this super simple model, just lattice of pendula, we get particles, quantized particles, we get pair creation, annihilation, you get entire Lorentz special relativity, Lorentz invariant, time dilation also. So this is a good starting point to think about particles, yes, as the field configurations, not just some abstract creation operator effect, but very real field configurations. So now to go to 3 dimensions from 1D, there is this very nice similarity between electromagnetism and hydrodynamics. Yeah, so if you look at the equations, especially for superfluid without viscosity, the equations governing electromagnetism and hydrodynamics are nearly the same. Yeah, so there is this analogy. The main difference is that here is speed of light, here is speed of sound. But the equation is very similar, and there are many effects related, like this Barnett effect, saying that a rotating object, even without charge, it gets magnetic field. There are these nice relations like here that we have. It relates velocity, the A field of electromagnetism, and the change of quantum phase. Yeah, so quantum phase is also some kind of rotation or some degree of freedom, like I mentioned. Yeah, so electromagnetism is here, the tilts of the long axis, and there is still this twist, this angular momentum. and we need to relate them in equations like this, well-known equations. So in this analogy, for example, the Lorentz force becomes the Coriolis force. The A field becomes some velocity. The magnetic field becomes the vorticity. So there are nice realization, for example, of Aharonov-Bohm effect in this analogy, or even the Zeeman effect. So there are these very nice experiments with bouncing droplets. I think I have some slide, or maybe I'm not. So that they have this vibrating plane, and there is a droplet, and this droplet acts as a classical object wave-particle duality. It is coupled with waves it creates. Yeah. So and they get many quantum-like effects for these classical wave-particle duality objects. For example, orbit quantization, like here. So if they look at the space of these orbits for these droplets, this is not continuous. The radius turn out the discrete. They get orbit quantization because this couplet wave from these droplets has to become standing wave. So we get the resonance condition exactly like in stationary Schrödinger equation. Moreover, they get this Zeeman effect, like using the Coriolis, that if we rotate this tank of liquid, they get the distance shifts left or right. So it sounds obvious as some centrifugal force, but this is literally the analogy between the magnetic field and the rotation. Yeah. So we get really mechanical intuition for Zeeman effect using this hydrodynamics, electrodynamics analogy. Okay, so we have this analogy, electromagnetic hydrodynamics, but there are missing particles. Yeah, so the question is how to add the particles to this analogy, and liquid crystals provide the answer. And there are many articles showing getting Coulomb-like interaction, that they build these topological charges like here. So here is +1 topological charge, -1 topological charge, and looking at distance versus time, they get long-range interactions, and we will show in a moment that we can get exactly Coulomb interaction. And if we have Coulomb interaction in the Lorentz invariant model, then you get the entire electromagnetism. Yeah. So to summarize, so there is this analogy between electrodynamics and hydrodynamics. Even in QCD, they say this is most liquid, most super fluid. Even they smash this nuclei in Large Hadron Collider. Yeah, so this is fluid. This is super fluid. And now we need to add particles, and in liquid crystals they add these particles with quantized charges as topological, and we can get effective Coulomb interaction. I will talk about in a moment. So yes, so we have this analogy of dynamics, hydrodynamics, but it misses particles, which can be obtained in liquid crystals. So this is a very good direction to understand particle physics. Going to space-time, you get also the gravity with the teleparallelism interpretation. Okay, so let's think about these topological defects we can get in liquid crystals, generally in just three dimensions. So in one dimension, we get just these kinks, as I have mentioned, like Stein-Gordon model. Then we can get vortices, and finally in 3 dimensions we can also get these point-like charges. Yeah, so those, as mentioned, will be interpreted as electric charge, but we also need the vortices. And turns out, I talk about it, they are required, for example, in quantum thermodynamics for the quark strings. That you have quark-antiquark pair, like here, quark-antiquark pair, and they are connected with some one-dimensional structure called quark strings, having large energy, having energy growing linearly with distance. Yeah, so to understand quarks, we need to both type of topological defects, both the point-like for charge, but also vortex-like for topological for quark strings. And moreover, these two should be sufficient, because in Large Hadron Collider, again, they use so-called string hadronization. Yes, string hadronization. This belief, like here, basic model, standard model, that indeed there is created this large string, these quark strings in the collision of the smashing two nuclei, and this string decays into particles. Yeah, so these two topological defects should be sufficient as the basic building blocks, and we just need to understand what the vortices can decay into and compare what they see from decay of the quark strings. Yes. So I will discuss it. So here are some. Please interrupt me. If there are some questions, comments, please interrupt me. We can discuss. Okay, so here are some more arguments that we need these one-dimensional structures called because of vortex and topological vortex. So, for example, in sun's corona, they see these shining lines. Yeah, so there are really shining one-dimensional structure. And if you look at the book, this physics of these magnetic flux tubes, they say that it's not well understood, but they suspect it might be topological nature. Yeah, so the question is, what are these shining lines? And it's probably there are some topological vortices. And from another direction, we need these quark strings, but there are also these so-called halonuclei. That there are some nuclei like lithium-11 that you have the core, and two neutrons in very large distance. And so the question, and it is bound for milliseconds. So it is very stable structure. They call it Borromean structure. So the question is, what binds them? So maybe this quark string being some topological vortex. Okay, so we need these topological vortices generally. Yes, called this Ablikosov vortex. So there are this perfect liquid quark-gluon plasma, but many vortices are these quark strings. So here is this view on this quark anti-quark pair. Yeah, so we have this quark string as topological vortex, and if we rotate this field, like here, this inward-outward rotation, then we get, if we rotate by pi, then we get a hedgehog. And hedgehog for us is quantized charge as electric charge. So, but you can perform a fractional rotation, like pi third. So this way we get fractional charge. We get, like quark, we get fractional charge. However, it brings some conflict between them. There is something strange going on here, so it has large energy. Yeah, so we can do it, but it has large energy, and indeed growing linearly with distance. And we know that there is this corner potential that indeed there is Coulomb. If we have two quarks for small distance, this is approximately Coulomb interaction because there are charges, and then you have linear behavior. Yeah, so and this conflict has linear energy dependence with distance. Yeah, so we have just derived on picture the corner potential. Yeah, so first we have Coulomb because there are charges, then we have linear because there is some linear energy density conflict between them, created by this fractional charge against the charge quantization. So yeah, so we can violate the charge quantization to integer charges. However, this is costly. The cost is this linear cost per distance between the two quarks, known as this corner exclusivity potential. Okay, so as mentioned, there is this halonucleus. Yeah, so I have mentioned that there is this core, and there are two neutrons. Can be neutrons, can be protons. But there are bound for milliseconds, 700 milliseconds, 100. So this is much larger distance than nuclear force. Nuclear force is like below 1 femtometer. Here we have like 5 femtometers. So the question is, what binds them for extremely long times? So I think the only answer is this quark thing as topological vortex. That literally there should be some topological vortex going here. Okay, so this classical quantum. So maybe let's briefly talk about it. So the question is, where is this distance? So we have classical physics, we have quantum physics. The question is, where is the boundary? So I recently I've seen some survey that half of physicists say there is no boundary. So and I think there is no boundary. Let me briefly explain why I believe there is no boundary. So let's think about these Capet oscillators. Yes, we can describe them classically like these simple equations, but you can go to normal modes, and the equations becomes literally unitary evolution. Yeah, so we get the same system from perspective of classical physics and from perspective of quantum physics. This is practically quantum physics. Then we can go to lattice, the crystal. Yeah, so we can use classical description, but we can go to phonons, go to normal modes, which in quantum field theory are treated as real particles. Yeah, so this is just different view, but so this is the same but different, just different perspective, classical and quantum perspective. Then in this infinitesimal limit, as mentioned, they also get quantized orbit, for example, in this bouncing droplet, because this couplet wave has to become the sounding wave. And finally, we need this varying number of particles in quantum field theories, and in soliton models, we get it. Yes, we have 0 particles here, and now there is positive topological charge and negative topological charge. Yes, we can continuously, through continuous process, we can create pairs of electron positron, for example. Yes, so with Feynman diagrams, we can represent them in abstract way, but still there should be some hidden field configuration, and we can ask for this field configuration, and topological solitons bring a very concrete approaches with quantized charges and pair creation and so on, already in this one-dimensional Sine-Gordon model. Okay, so yes, so here I have these experiments with this bouncing droplet. Yeah, so they have many articles like this interference for double slits. So they have these single droplets, and they look at statistics. They get the droplet. They get interference patterns of the double slits. They get orbit quantization, also double orbit quantization of two quantum numbers, distance and angular momentum. Recently, they also get this CHSH, this Bell-like inequality evaluation. So the question, so finally, if you have these topological objects like these vortices, for vortices there are also quantum-like effects observed, like this interference, like Aharonov-Kasher, which is like Aharonov-Bohm. There is tunneling. So generally, these topological objects also behave with require quantum-like description to effectively work in them. Yeah. So, but there still are concrete field configurations. Okay. So here are these topological charges. So in 2 dimensions we have this, let's say, the vector field, and to calculate the topological charge, we go around this singularity and count how many times the field rotates. Yeah, so here the field rotates once when you go around. Here also once, but you change the total phase, like in Gauss invariance. Here, if you go around, the field rotates -1 time. So this is -1 charge, topological charge. Here it rotates twice, it's +2 topological charge. But here it rotates 1/2. Yeah, so if you go around, the field rotates 1/2 times. So there is some magic. So did you violated the topological charge quantization? So no, because if you rotate by pi, the field rotates by 2 pi. The field rotates by pi. The field makes rotation, but it is the same field. Yeah. So you have a field which is the same after rotating by pi. It's like an ellipse. So using this natural for liquid crystal, so this is well known in liquid crystals, that if you use a molecule which is the same after pi rotation, then you get 1/2 topological charge, like spin. Yes, and for spin, literally there is this quantum rotation operator saying that spin S particle rotated by theta angle makes that quantum phase rotates by theta times spin. So this is exactly what we have used here. Yeah, so this is exactly, this topological charge is exactly according to the definition of spin. So, but we can also have spin 1/2. Yeah, so this is spin, this topological charge in 2 dimensions as a cross section, but in 3 dimensions we have this point like. So this is electric charge, this is spin, I believe. Yes, so it agrees with quantum rotation operator. It corresponds to magnetic dipole moments. We can have 1/2. So this agrees well with spin, also being quantized, but to 1/2. And for point-like in 3D, we get electric charge quantization. Okay, so here is this. This mentioned Gauss law and its topological version. Yeah, so we have the Gauss law, which calculates the charge inside some surface S, and by integrating electric field. The problem with this Gauss law is that it returns a charge being a real number. Well, in nature, it should be integer number. beside quarks, I have discussed. Yeah, so the quarks can break it because there is this linear quark string singularity, like the vortex. But generally, it should be integer. Yeah, so we need to replace this Gauss law to Gauss law, which has built-in charge quantization, and there is this topological version, is Gauss-Bonnet theorem, which is not the same, but uses this curvature as electric field. Yeah, so this is the Faber's, Manfred Faber's, I collaborate with approach that we have some deeper field, like this N field, like second axis of your tetrad of the teleparallelism. We define its connection as A field, its curvature as F tensor, and use standard electromagnetic Lagrangian for this F tensor. This way, I'm showing in a moment, we get a Gauss law. We get the Coulomb interaction, and it is Lorentz invariant, so we get entire electromagnetism. So also, we require that we use dual formulation. So if we don't use dual formulation, these would be magnetic monopoles. But we don't observe magnetic monopoles. We only observe electric monopoles as charges. Yeah. So this is the main problem with these people looking for monopoles. I believe that they use wrong formulation. They should go to dual formulation, and now everything agrees, because we observe only electric monopoles and magnetic dipoles. Not the other way, because I believe we need to use this dual formulation to switch magnetic monopole into electric monopole. Okay, so here is some simple derivation of Coulomb interaction numerically. Yeah, so we create this configuration with two charge and the same charges, plus and plus charge in various distance. Here with opposite charges, so plus minus. Yeah, so here is plus topological charge minus topological charge. And we integrate Hamiltonian to get energy of these configurations for these various distances. And they are the dots. Yes, calculated with this source with Mathematica. And we get the dots, and the line is defeated 1 over R. So Coulomb potential. So we just derive that indeed by this calculating energy through integration of Hamiltonian, we get effective Coulomb interaction between these topological charges. And moreover, this is Lorentz invariant theory, so we would also get the magnetic field. So this way we get entire electromagnetism for these topological charges. So electromagnetism with built-in charge quantization as topological. So better than standard one. But as mentioned, there is also a problem in the center of such singularity. Yeah, so if you would have the hedgehog going down to 0, it would have infinite energy. Exactly like infinite energy of electric charge, of electric field of electron. Yeah, so there is a problem in the center, and Higgs potential allows to solve this problem, regularize the singularity. Yeah, so let's start with the simplest Higgs potential. That it prefers unitary vectors, but allows them to deform. Yeah, so using just unitary vectors, we would get discontinuity in the center of infinite energy. But thanks to this Higgs potential, it can deform to 0 vector in the center. Yeah, so if you look at energy, so here is some energy plot. So the red line is without it's just electromagnetic, like this energy of electric field. It would go to infinity in the 0 without regularization. Instead, it activates the potential field, the blue one. And tangential means that the derivative changing the distance, the length of this vector. So to prevent the infinity, there are activated these two terms, so that the final energy of such quantized topological charge is finite, and should be 511 keV for the mass of electron for electron. Yeah. So indeed we get this. We can regularize the singularity. So there is no need for singularities. And if you look at energy of electric field around charge, like elementary charge, if we integrate it from 1,4 femtometers, then you get the mass of electron from its electric field alone. So we see that electron cannot be perfect point. It needs some deformation in distance, like a few femtometer distance. It needs some deformation from being perfect point charge, not to exceed mass of electron with energy of its electric field alone. Yes, and indeed we get this kind of deformation like here. Yes, so here is this Faber's approach. And this deformation turns out to brings very slight deformation of Coulomb interaction for two charges being very close. Yeah, so where this regularization. So here is Faber's from this article. I think this article. Yes, so this article. So here is the Coulomb. The blue line is the Coulomb potential, and the red dots are the energy he got for very small distance. These are 20 femtometers. Yeah, so we can see that the Coulomb interaction becomes stronger for very short, very low distance. That means very high energy, and this is known as running coupling. That for very high energy, the alpha deciding the Coulomb strength grows, becomes larger. Yeah, so we should expect this kind of effect. So to summarize, we not to exceed mass of electron with its electric field alone, we need some deformation, and including this deformation, we get deformation also of Coulomb interaction, which exactly is in agreement with the running coupling. So there is no need of magic. We can understand everything in classical physics before the second quantization. After second quantization, it's called a randomization procedure, which subtracts this infinity by hand. So if you ask where it subtracts this infinite energy, we should get this kind of deformation of electric field of electron. So now we can ask about some experimental boundaries of size of electron. So if you look at usually people talk about this G factor. It's from Delmert 1989 article. So here is the plot he's used. So here is the G factor -2. Here is the radius. So he plotted three particles. So proton as made of 3 quarks, triton as made of 3 nucleons, and hypothesis that electron is made some 3 partons. So probably he started with line for electron, but using line, you would get a negative radius for electron, so it makes no sense. So instead, from 2 points, he extrapolated with parabola. So yes, so this argument makes no sense. So he has calculated the factor very precisely and used it to motivate the size of electron. But if your student would extrapolate from 2 points with parabola, student would not pass. But Nobel Prize winner can do it. Yes. So let's think about more serious arguments. So the most serious, I think, is electron positron cross section, and here is this cross section for electron positron. So here we can see that there is a line in log-log plot, but this is very high energy. This is GeV. Yeah, so this is 10 GeVs, 100 GeVs. But we are interested in size of the resting electron. So we should take this line and extrapolate it to resting 2 times 511 GeV mass of resting electron plus positron. If we do it, we get like 100 millibarns. So it means like 2 femtometer distance. Indeed, if we extrapolate this line to resting electron plus positron, we get as required distance not to exceed mass of electron with an energy of electric field alone. Yeah, so everything seems to agree. Yeah, so we need to do this extrapolation because we are not interested in size of high energy electron, but of resting electron. If we do it, we get similar distance like required not to for deformation not to exceed mass of electron if it's electric field alone. And additionally, there is this running coupling that perfect point charges would not have this deformation of Coulomb interaction running coupling, but real electron have. And indeed, if we include this deformation, we get this deformation also in running coupling deformation in Coulomb interaction. Okay, so there are similar models, so-called Skyrmion model. Okay, how much time do I have? I don't know. So should I don't know. Maybe I talk too slowly, or please interrupt me generally. Okay, so there are these popular Skyrmion models. They are quite similar, but with different interpretations. So they interpret the topological charge as baryon number instead of electric charge. And they have only short range interaction. They don't have electromagnetism. And there are many problems with this approach. So baryon number cannot be validated in this model, but it is believed to be validated both in baryogenesis after Big Bang, that there was located more baryons than antibaryons, the Hawking radiation that we can take baryons, beat a black hole, and it will radiate without baryons, massless radiation. So there are many people working on that, but I think there are many arguments against it, and it doesn't have electromagnetism. So I think the much better interpretation is topological charge as electric charge, quantized, and to get the long-range interaction, we need this Higgs-like potential. And now let's go to the gravity. Finally, yes, as you are most interested in. So finally, if you think about this field not in 3 dimensions but in 4 dimensions, the field can have undergo four type of dynamics. Yeah, so we have this tilts type rotation. Yeah, so we have this elongated molecule. It can have high energy tilts, also low energy twist. Yeah, so because, for example, in QED Lagrangian you have high energy term for electromagnetism and low energy term for quantum phase evolution. But also, finally, in 4 dimension, we need also the boosts. So if we include it, we get second set of Maxwell equation, I will mention in a moment, and it's exactly this gravity electromagnetism. Yeah, so we will get, so from relatively large tilts of this second axis, we get electromagnetism, but for boost, there will be really tiny boosts. Yeah, so to get a large boost, we need to be close to the black hole or something. Yeah, so usually these boosts are really tiny. So the contribution has to be much higher. So the length of this axis, time axis, should be much longer. And so what is curved is the space. What is perpendicular to this time axis? Yeah, so this time axis has very small perturbation, and the perpendicular plane is the curvature of the space. And for space-time, we don't need curve for space-time here. Yeah, so only space is curve in this view. Space-time can be flat, and many cosmological models say the space-time can be flat. And we also get this interaction, electromagnetic gravity interactions. For example, in high gravitational field, the electromagnetic propagation should slow down. Yes, if you have slowed it only down, it's also studied by Dicke, but Einstein also. If we slow down electromagnetic propagation in gravitational field, we also get this gravitational effect, like light bending by Fermat principle or time dilation, because all chemistry, biology is made of electromagnetism. Yes, so this is alternative way to view both the gravity, both the interaction, the gravitational effect, like light bending, time dilation. Okay, so I think this is the most interesting from your perspective. I will discuss. Okay, so here is some discussion about this unification between the tilts and twists. You have it in many places. We have this like momentum operator has a derivative, but for A it is not derivative, but in this view both are derivatives, and literally this spatial rotation unify both. Yeah, so you have electromagnetism, and electromagnetism is believed not to be fundamental, that we have deeper A field because of the Aharonov bomb, for example, and here is saying that we need even deeper field because of a lack of charge quantization. Yeah, so here we don't have charge quantization. Charge can be a real number, or in nature it's integer number. To get charge quantization, we need to use an even deeper field and define its connection as A field, curvature as F tensor. And this deeper field is your teleparallelism. Yeah, so these are in 3 dimensions. There are 3 axes, like in liquid crystals. In 4 dimensions, we need to add the temporal axis. And there are similarities between electromagnetics and hydrodynamics, like in Aharonov bomb, using with electromagnetics very similar to this mechanical magnetism as vorticity, A field as velocity, Coriolis force as Lorentz force. Okay, so here is the final Lagrangian, and maybe I talk very briefly about this unification. Yeah, so I've mentioned this is the final Lagrangian I'm using as candidate. So we have these electromagnetic terms here, the Higgs-like potential, both to prefer these lambdas, the shape of our molecule, the length of the 3 axes, and also allowing to regularize singularities, for example, in the center of charge. But this F tensor, in fact, is curvature of this deeper field. Yeah, so we have this is your 4 vectors of teleparallelism packed into a single tensor, and we define its curvature as our F tensor, and use standard electromagnetic Young-Mills like term. Yeah, so and the different lengths correspond to the gravity plus electromagnetism plus quantum for this with Kyle-Gordon-like equation. And within, yeah, so here is this unification. And if we look at this F tensor, if we expand it with the curvature, so here is this final this F tensor. Yeah, so here is the so this R1, this curvature corresponding to electromagnetism. R2 is much smaller, multiplied by delta as Planck constant. So this is the quantum mechanics, like the interaction between electromagnetism and quantum mechanics. Also this curvature, which includes this twist. But also from boost we have another curvature. So tilde, R tilde means that it's not for spatial rotations, but for boosts. So from curvature of boost, we get also this kind of term. So we get a second set of Maxwell equations for gravity. Yeah, so they nicely unify. And moreover, okay, so so there are also these terms like here. So there are very interesting terms, because in Hamiltonian they get negative contribution, and this will be crucial for the clock of the particle. Yes, that the resting electron and resting neutrino already oscillates. Yeah, so in this model, the explanation is that that having this kind of Lagrangian, this f mini, but 4 indexes, if we transform to Hamiltonian, then we get both positive and negative terms. The red are positive, the blue are negative terms because of space-time signature. And these negative terms gives preference for the oscillation, so non-zero time derivative for the electron, for the neutrino. Yeah, so this is crucial, and also for the gravitational mass. Maybe let me talk further. So okay, so here is this toy model for the clock. Yeah, so the question is why a resting electron and neutrino would like to oscillate. That's a very important question at the heart of quantum mechanics, I believe. So yeah, because if you have this oscillation for electron, then it should create the couplet waves, and these couplet waves, you get the duality. The couplet waves will lead to quantum-like properties, for example, like these bouncing droplets. Yeah, so it's absolutely crucial to understand why a resting electron has the clock. It will lead to the waves, which brings quantum effects. Yeah, so here is some model I'm using. So here is the toy model, and then there will be full model. So this toy model is inspired by this full model I have mentioned. So here is this full model, these negative terms, and his toy model to understand the mechanics and so briefly get what's happening there. So we have this problem that in relativistic quantum mechanics, mass literally propels the clock. Yeah, so that if you have this quantum phase evolution as energy, we need to put the mass. So resting particle already has oscillations, and it is confirmed for electron, for example. And there is recently popular time crystal field that they search for object which in lowest energy already oscillates. So like pendulum is not, because you can slow it down to 0, but electron and neutrino satisfies this property. Resting electron and neutrino already oscillates. So here is the toy model, how to get it. So here is the standard, this phi to phi model, like Saint Gordon. So we get this particle are going from one minimum to another minimum, and this shape hides energy, mass of the particle. Yes, and now we'd like to make this kink time crystal, to make it oscillate already resting. So how to do it? We can add these kind of terms, these curvature square terms, as mentioned, with negative term, with minus. Yes, also I can mention that naturally that this plus can get electromagnetism, gravity electromagnetism, but there will also appear this minus, this negative, these blue lines, they can be also minus. So if adding minus here, what's happening here? So now we have this quantum phase, this psi, and the phi as our field, our shape of particle, you can say. Yeah, so we have shape of particle. These are the derivatives. So here is spatial derivatives. So if you have particle, this spatial derivative is non-zero, and now it brings energetic preference for non-zero derivative, temporal derivative for this quantum phase. Yeah, so literally in the presence of particle, when the phi1 derivative is non-zero, there appears tendency for time evolution. Yes, so exactly what we need, that literally the mass of the particle as its structure, field structure, brings energetic tendency for the clock of electron, of neutrino finally. So here is the energy dependence. So we can see that energy for resting king energy is like 2,9, but for when you allow for oscillations, the energy drops to 2,3 or something. Yeah, so it's not below zero. It's some small. So this mechanism allows resting particle as field configuration reduce a bit its energy by turning on oscillations. It's non-zero omega. Yes, so exactly as we need for electron from neutrino. So here is the time model, one-dimensional time model, and here is this full model. So as mentioned, you have this F mini. So if there is just F mini, going from Lagrangian to Hamiltonian, you get only positive energy. Yeah, so this is well known for electromagnetics. But if you have four indexes, there appears going from Lagrangian to Hamiltonian, there appears both positive and negative terms. Yeah, so we get both these positive curvature terms, as mentioned, required for electromagnetism and for gravity, but we have also this blue, these negative energy terms. And what you can see in these blue terms, so these are the most important, this clock propulsion, literally. Yeah? So gamma one means twisting, and no in direction, if it's zero, then it's with time. Yeah, so and gamma 3 tilde means boost. So here is in space, here are the boosts. So this term, which has negative contribution in Hamiltonian, brings preference of time evolution and boosts. Yeah, so it brings both. So we have these particles as quantized as topological charges, but still we don't know why they have also gravitational mass. This is very non-trivial. We get electric charge for Coulomb interaction from topology, but gravitational mass is not quantized, is much smaller. So the question is why it also has gravitational mass. And this kind of terms allows to understand it, because the particle can a bit reduce energy by activating this kind of potential. Yeah, so which has both the boost for the gravitational mass, but also the gamma 1 for the clock of electron of neutrino. Yeah, so I think this is crucial to understand both why particles has not only interact through Coulomb interaction, but also with Newton interaction. Yeah, so gravitationally, and why they have clock. Okay, so now I can briefly go to further particles. So why we have I have talked about electron, let's say like here, but why we have three leptons. So why three leptons? Because we live in three-dimensional space. Yes, because if you have hedgehog, you can perform hedgehog with the long axis, but maybe of the second axis or the third axis. We have three different axes. Yeah, so asymptotically, this is the same topological charge, but different regularization, different deformation. So the same charge but different mass, like three leptons. Yeah, so as we need. Then, as mentioned, we have the quarks as excitation of the quark strings, connecting the two quarks. And I have also mentioned about the string hadronization, that they believe that in LHC there is this basic model to understand what they see in these collisions of the particles, and they believe there is created these quark strings and it decays into particles. So to understand which particle corresponds to which configuration, we should just take a look what they see in LHC collisions and what topological vortex can decay into. Because quark strings, if you ask for non-perturbative view, is topological vortex. So let's think about what topological vortex can decay into. So first of all, it could form the simple loop. Yeah, so this is unavoidable. This would be very light and stable field configuration. As we can see, it can be in three families because it can be looped around one of the three axes in 3 dimensions, and it can oscillate between each other because it's just rotating the field continuously, and it should be very stable and light. So it is much more stable than photon. Yeah. So while photon cannot pass through Earth, neutrino can pass through Earth. So we need some stabilization mechanism and this has topological stabilization mechanism, which should allow it to pass through to Earth like neutrino can. And then we can get a simpler knot. Yeah, so we have one topological vortex, a second vortex around it. So what we can see that this vortex around it, yes, this cross section, the vortex around deforms the field of the central vortex, and deforms toward the hedgehog. And hedgehog for us is topological charge, as electric charge. Yeah, so we can just enclose this hedgehog for proton, and but for neutron, so he would be the simplest baryon as proton, but for neutron, this positive charge has to be compensated. So for neutron, we get plus in the center and minus minus. Yeah, so and we can now explain why proton is lighter than neutron, because a proton can just enclose the hedgehog, and neutron has to compensate it, and this compensation means a larger structure, means additional energy. Yeah, so we have just explained why proton is lighter than neutron, because baryon itself has this tendency for charge to the structure. Proton can just enclose this tendency into entire charge. Neutron has to compensate it. Also, if you have this loop of topological vortex, it could form this twist like Mobius strip. Yeah, so this is also unavoidable. And if we take a look at the decades of strange baryons, it turns out it nicely agrees with strangeness. This number of twists which can be released through it seems to nicely agree with the decades of the strange baryons. Okay, so here we have the neutrinos, the baryons, neutrinos. So as mentioned, the simplest knot for baryons. Proton is lighter than neutron because it can just enclose. Then it's required deformation. Neutron has to compensate it. We can get 6 quarks because some have this loop around, some don't have, and so we generally can understand particle physics. Also this. Also, for example, why deuteron has, so it's very not clear that why the deuteron has electric quadrupole moment. Yeah, so if you think about deuteron, just proton and neutron, so proton is 0, first proton is plus, neutron is 0, so it shouldn't have electric quadrupole moment. But experimentally, deuteron has large electric quadrupole moment. And here indeed we have plus due to baryons, plus due to baryon, and now 0, so we get electric quadrupole moment. So it can explain why proton is lighter than neutron, why deuteron has electric quadrupole moment. Also, then with neutrino, also there are, so I can talk about neutrinos, but maybe let me skip it. So this halo nuclei, as mentioned, that there are some nuclei which are much larger than we can explain. So it seems that this topological vortex is crucial here. There are some problems with the standard views, and this model can explain, but maybe let me skip it. So here is the summary of these topological defects and particles. And so okay, maybe I think, I don't know, so maybe let me 1 hour has passed, so maybe let me finish now. Okay, maybe the literally last slide. So here is my last slide. So generally, finally, there is the standard model. Yeah, so here is the Lagrangian standard model. So this is huge, and maybe one can think about this epicycles that something didn't work, so they added more and more terms. So, but the question is, could we simplify it? And more importantly, this is a perturbative Lagrangian. So it has creation operator saying that magically particle appears. It has probability distributions in Dirac terms. So the question is, can we find a non-perturbative Lagrangian which works only on fields? And this kind of, as mentioned, this kind of Lagrangian seems to do it. So we have this electromagnetic-like, Young field-like term, which unifies electromagnetic, quantum mechanics, and gravity. And we need this Higgs potential, both to regularize singularity to make non-trivial vacuum. And it gets the unification, it gets the particle as topological defects in promising way, and hopefully its effective description should be this close to standard model Lagrangian. So that's the goal, but it's quite difficult goal. So I'm looking for collaboration to go there. Okay, so thank you for attention. So maybe let's discuss now as 1 hour has passed.
Tá sem som, Rodrigo.
Okay. Hello. Okay. Luiz Gustavo, do you questions?
Yes, I have some ones. I'd like to, first of all, to thank the Dr. Judah by to be here presenting his work for us. Is a very interesting work. I have two questions only, because I'm still include. How could I say? I am still absorbing the new concepts. But first question I have is how to, if you have, how you choose the potential functions. How to choose?
Sure. So it should prefer this shape of molecule, the four lambdas, the eigenvalues. Yes, and so finally it should be this one is for electromagnetism. Yeah, so this term is for electromagnetism, and there is much smaller contribution of quantum phase evolution. So this h bar, this Planck constant, should correspond to this delta. So it is very close to zero, but not zero. So the twist is recognized, but very lightly. Yeah. So that this is extremely small, this Planck constant. Yeah. But then for G, I think it should be very large to get the boosts are much more costly. Yeah. So they should correspond this Planck constant and to gravitational 1 over gravitational, and they should be in the minimum of the potential. And the final potential, so the question is how to choose the final potential. So in Landau-de Gennes, they used, so here is the original Landau-de Gennes model. So they use this kind of potential, Higgs-like potential with traces and powers. So this one approach, traces and powers, and just encode the minimum, this preferred shape, this G and delta for Planck constant. Another approach is like here, that we have these capital lambdas as the preferred eigenvalues, and the lambdas are the current eigenvalues. But choosing the potential indeed is very difficult problem. Yeah. So this is for later. Yes. So there are like two basic approaches. Maybe there are the others should be considered. But this is a difficult. Thank you. Very difficult question. Yes.
And my second question is, I see that the work is very good qualitatively, but I'd like to know if you already have any insights of how to make predictive quantitatives, or how to make quantitative predictions. Is have already an insight?
Sure. So these are very difficult parts. So I have like this Coulomb interaction. This is quantitative. Sure, and they get also this defect, but it's also difficult. That this deformation through Higgs potential requires a bit stronger Coulomb interaction for very short distance, very high energy, which is in agreement with running coupling, as Matthew Faber has shown in his article. For others, yes, there are very few approaches, but this is really difficult, unfortunately. So I'm searching for help here. So some other, I think, for example, I have this Klein-Gordon like equation. I start with this Hedgehog as ansatz and treat the phase as a parameter that asks for its evolution and get this kind of Klein-Gordon like equation for this quantum phase. But and generally I get electromagnetism as second set of Maxwell equations. So this is I get very similar term in Lagrangian. So gravity electromagnetism. So there are a few small, but I need, if somebody would like to help, I would gladly collaborate. Say.
I'd like to say I like it very much, this work. I thank you for the presentation, and I guess it has very potential to future solving several issues of particle physics. I guess
this teleparallelism. And this dream of Einstein, yes, to unify electromagnetism with gravity.
Yes. Well, I'm satisfied with the answers of my questions. Rodrigo, se quiser dar continuidade.
Okay. Professor, excuse me your presentation in my screen. And okay, let's see. Opa, okay. Yeah. This graphomagnetism in teleparallel gravity. This work is in 2008 year and from Brazilian DF. This is the formal treatment in teleparallelism of gravitomagnetism. For me, this work is very important. Not very important. This principal reference in gravitomagnetism. And your work inspiring me for read this work gravitomagnetism and generated a synthesis to your work, professor, and this work. The vector polarization for me is a torsion, and for me, I need write a Lagrangian this type Lagrangian where it is torsion and its torsion is a function of polarization, vector polarization, and say it. My question is your opinion about this program and of study of survey.
Sure. So generally, we need finally electromagnetics. We need this F mini. So, but you use different tensor here. Yeah. So you have this torsion and the second tensor. But if you want electromagnetics, there is F mini. So maybe you can interpret with F mini. So here this F is curvature. So the A field. So you need to, if you want to unify electromagnetics, you need to answer what is the A field, what is the F tensor. Yeah. So and natural answer is that A field is the connection, curvature is F tensor. Thanks of that, your Gauss law comes topological charge of your vector field of your tetrad. So you get the charge quantization. So I think you need to use the same tensor here. You use different tensors, but I think you should use the same if you want electromagnetics also.
Eu vou compartilhar de novo. Então, so is the good way for a survey?
So I believe you need electromagnetics. You need to F mini. Yes, electromagnet. If you want electromagnetics, you need F mini. Yeah. So you need to get Coulomb interaction, preferably also charge quantization, so that your Gauss law counts topological charge. If you want that charge quantization, you need F as a curvature.
Okay. Não, em teleparalelismo não is curvature generator gravitational interaction. It's distortion.
Oh, and the distortion, I think, is also here. In the gammas, I'm using the distortion, that transporting given position, there is both rotation of the field, but also boosts. So yeah, so in the connection, sure, I have both, yeah. And now they are hidden in the curvature. So we have two connections, and now they are hidden in the curvature to make the Gauss law count the topological charge.
This is my. I searched F mini right in terms of the torsion.
Yeah. So
No,
you should try to go to this kind of form, like electromagnetis, and get the Gauss law as with built-in charge quantization, maybe as topological. Yeah.
I is here, is here. Gente, cadê? Apresentar, paradela, aqui, apresentar, aqui, compartilhar, and
Sure. No, yes. So you have the F, sure. So here we agree, but what is the A field? So for me, A field is connection.
and the field strength and the potential translation in in how many is the translation gauge potential in your work is the same things is
So in my view, A is connection approximately.
is exponential proximity.
A is connection and the curvature is F. Yeah.
This work is very small translation, but in this work he make for black hole in shoot solution and in here he make no small translation the tetrad fields.
Yeah. So Schwarz is the hedgehog for the gravity. Yes, in space. Of my time axis. Yeah. So your configuration of your teleparallelis, one axis is hedgehog for a black hole.
It's black hole. Do you know your working?
So I haven't worked on black holes, but generally hedgehog one hedgehog is electric charge quantized, and then hedgehog is the black hole for you for this time axis. So it has much higher energy. Yes, the energy of the black hole is much higher than of charge. So
Okay. No more questions. And I speak em português. Pessoal, tudo bem? Temos 5 pessoas assistindo aqui. Alguém tem alguma questão para o professor? Eu traduzo. Vocês podem perguntar em português, que o LG traduz aqui. O meu inglês é meio ruim, meio não, é muito ruim, mas ele está respondendo. Então, né? Mas o LG fala um inglês mais decente. Então, alguém tem alguma questão aí? no, I speak in the chat, and in this time is 4 people in
Five.
this live. 4 people watch
Five people.
this live. Oi, LG?
Você não falou que eram 5?
Ah, 5. São 5.
Five?
5. É que oscila.
Ah, sim.
Or 5 people or 4 people. Não. Então, no questions? No questions? Ok, enquanto vocês decidem, eu vou fazer o nossa merchandising. Nós temos, passando aqui o nosso apoia-se. Como vocês podem ver, a gente está fazendo questões, uma pesquisa, inclusive, com gente de fora do país. Esse é o nosso novo colaborador, o professor Jarek Duda. Então, e, assim, isso de forma tremendamente independente. O professor LG é da UFAC, mas nós só temos o carimbo legalizando isso aqui como um projeto de extensão, né? E a gente está conseguindo fazer alguns avanços científicos até a hora e tal. Então, nesse sentido, eu queria realmente reforçar o pedido de apoio financeiro a vocês. Essa semana eu tenho, inclusive, uma viagem a Cabo Frio para uma prova, para um concurso. Então, queria muito pedir apoio financeiro a vocês para essa viagem que eu vou fazer. Nesse sentido, vou voltar a falar em inglês. Futuramente, a gente pretende fazer legendas para nessa live. Assim, eu agradeço a presença de todos. Eu vou encerrar, vou passar a palavra para o LG em inglês, para ele fazer os encerramentos, e a gente vai agradecer ao professor Jarek Duda. Professor Jarek Duda, muito obrigado. Professor Luiz Gustavo Almeida, please, do you ultimate consideration?
Ultimate. Oh. I'd like to thank Professor Jack Duda by your time here with us. It was a very exciting presentation. I really liked your approach, and I hope we may see more about your work in the future. Maybe a collaboration more effective could begin with us. And we are now mas como é que fala despedir mesmo? Well, I'm letting for you to say your last words. Do you want to say anything before we finish the transmission?
Yes, thank you very much for this discussion and very nice. Please just contact me. I'm glad to discuss. I'm slowly work. So I work on that since 2009. So this is a long time, work. If you have any ideas, we can discuss. Sure. So please contact me. I'm glad to collaborate here.
Okay. And apologizing about very bad English. Ok. Vamos encerrando, então. We end the transmission, end the live. Thank you very much, Professor Jarek Duda. Muito obrigado, Luiz Gustavo, por estar sempre por aqui, supervisionando e ajudando o nosso projeto. E sejam sempre bem-vindos. Welcome and frozen domains em Aether Tenebris. Até mais, pessoal. Bye, bye.
Bye bye.
Thank you.